recording a new OBS. And so what, as you know, if you go, okay, well, let's see, where are we? Did I publish that? Okay, I guess I did. Let me, okay, so we're here working on the agenda. So agenda for 4/22/20, and let's make a little list here of things that might go on the agenda. I think it's going to be fairly simple today. I'm going to say, you know, let's do chapter 17. Let's do it the whole way through, and then maybe start chapter 18. I don't know. We can also talk about the nobody problem. I mean the end body problem. Is there anything else people want to talk about? Yeah. Okay, we've got 8 people in here now. Shall I look to see who's joined us? Coin, Jason, Juan, Logan, Mario, Mark, and Michael. Great. Okay. Yes, good afternoon. That it is. Okay, so I'm going to minimize the participants. And, you know, we can add to the agenda. If people have other things they want to talk about, let's bring it up either with the microphone or in the chat. I'll be monitoring the chat as usual. So, as I was saying, what I usually do is, well, let's see, if we go to discussions, you'll see that this discussion is not pinned yet. So what I typically do is pin it and then move it to the top. I don't know, maybe the bottom is supposed to be the top, but I think of the top as the top. So that's where I am. And okay, so if we open this up here now, so yeah, the announcements, discussion, assignment. You know, I know some of my colleagues are doing this module thing. I don't even see the mod here, this modules tab. And I started, you know, if you go down there, you'll see that there's some historical things. Not hysterical, historical. And, okay. But that's mostly history. So, you know, I try to just keep up with what we're doing in the discussions. And the assignments will be updated. You know, I've been working on my open math and producing some material there. And when that becomes available, I will make an announcement, which will probably be, you know, over the next few days. You can look for those. All right. The idea being we need to sort of build up a war chest of templates for midterm and final. All right. So what do we have so far today? Oh, chapter 17, right? So for that, I think we can go to... Oh, that didn't work. Oh, that is that. Okay. Yeah. Vector in the free store. All right. And I think we left off at about... where was that? 17.4.5. So let's go there. And, you know, we can maybe, you know, I think we kind of dealt with the Void Star thing earlier on when we were doing some steganography. Do you remember that? With the Ada Lovelace picture. If you go to the calendar, let's see, can we go to the calendar? Where is that? Oh, this is the wrong calendar. Yeah, you look back here. This is this Ada Lovelace thing, right? And there was some steganography. And I had suggested that maybe I would do more of that as we get into chapter 17. And yeah, this is sort of hiding messages in pictures. I think that's kind of fun. And in particular, if we could do sort of a Morse code thing with Huffman tree encoding. That would be in the pocket for where we are. Okay. And I posted some old midterms here. Oh, where is that? Can you see that? Yeah. Which I forget. Should we open up one of those and see? Oh, those are problems. Oh, I see. Those are solutions. I forgot what I was. I mean, wasn't quite realizing what I was doing there. I will post some old midterms, and in addition, I'll probably use those to try to make my open math problem templates. All right. Anyway, back to, I'm trying to use these hotkeys here. Yeah, that's the problem thing there. Okay, so F9. Okay, and so if we go to that in 17.4.5, initialization, did we talk about that? So, it's kind of a show and tell reading hour, where we read all about how you need to eat your broccoli. And your carrots and peas. It's healthy. So the idea being that, a lot of modern programming, it's all about hiding memory management, right? But at the core, you need to know how these things are built. I guess first and foremost, so you can effectively use them, and then so you can build your own as needed, right? And oftentimes that is what computer scientists do. So we would like to ensure that an object has been given a value before we use it, right? So we talked about this extern thing, and I was also noticing the use of static variables in that pool game. And those are kind of related in a way. In any case, having to do with scope and definition versus declaration. And those are some slippery concepts. So, we'll maybe have a quiz on that. Then I wouldn't learn it. In any case, we want to be sure that our pointers are initialized and also that the objects they point to have been initialized. So consider this code here. So here, we were talking about this, right? So here you've declared P0 to be a pointer to a double, but it's uninitialized, likely trouble. And P1 is allocating memory on the heap, right? That's the meaning of the word new. So what are we allocating on the heap? Memory for one double, right? So, I would like one double. One double to the man at table 5! That was a reference to the one meatball joke, which, never mind. So P1 is a pointer to a double, but it's not, it isn't initialized. Why is it initialized? It's not initialized. But we have allocated memory for it, right? So it's allocated, but it's uninitialized. So that is, there's a memory location on the heap, right? For that, whereas this would be in static memory, right? Okay. And maybe okay. And this third declaration here, we're declaring, again, just one double, right? But now it's initialized. It's got the value 5.5. And here, this one is an array of 5 doubles. All of them will be uninitialized. Although double has a default value that kind of makes sense, so it could be a compiler will say, well, if you're not going to initialize a double, but you're going to allocate memory for it, I will make them all zeros. Or maybe that, happenstance leads to the memory locations having 0 in the first place. So sometimes it's hard to tell how they got to be 0. Consider then what this would be. Warning! Danger, Will Robinson. This will assign 7.0 to some location of memory. We have no idea which part of memory that would be. right? Oh, well, it's somewhere in the static memory, I think. Oh, did I say static? Stack. Where was that? Vector basic memory. Shall we go? Where is that little bit of? Yeah, stack. Right. I think this is stack memory. So what goes in stack memory? Static data is. It's easy to get those confused because they both start with star. So. Global variables are in static memory, right? So they have global scope and they're going to stick around no matter what, so they have static cling. Whereas when you call functions, they need space, so your call stack is in stack storage. And also local variables are in stack storage, right? So depending upon the context of where are we? Trying to maintain my thread here. That's what I get for jumping around, right? Well, yeah. So let's go back to this. So when you assign a value to an unknown memory location, that could be harmless, but never rely on that. Sooner or later, you're going to get the same result as an out-of-range access, and you'll wonder, why is my program crashing, or giving me the wrong output, or a scary percentage of serious problems with old-style C++ programs is caused by access through uninitialized pointers and out-of-range access. We must do all we can to avoid such mistakes. Okay, so memory, a little warning. Memory allocated by new is not initialized for built-in types. Okay, there we are, warned in writing. If you don't like that for a single object, you can specify a value. Okay. This contrasts with the use of square brackets, right, for an array. Okay, so notice that, right? We can specify an initializer for an array of objects allocated by new, for example, here, right? You don't have to put an equal sign. You just, right next to the declaration of an array of 5 doubles, you put an array of at most 5 doubles. If you put fewer, what happens? Well, that's a good question. I suppose we could experiment and see. Without the new, I think they get zeros, right? They get a default value. Or that's true for a vector, right? But for an array, and an array allocated on the heap, so this array doesn't know how big it is, but it does because we initialize it, right? So so P5, the number of elements can be left out when you initialize. Okay, so as usual, we should worry about uninitialized objects and make sure we give them a value before we read them. Beware of compilers that often have a debug mode. Uh-oh. That's you, Visual Studio. That's we who use it that way. Where the default initialize every variable to a predictable, often 0 value happens. But that implies that when turning off the debug features and when running an optimizer, or simply when compiling on a different machine, a program with uninitialized variables may suddenly run differently. Don't get caught with your variables uninitialized. That could be undefined behavior. Okay, when we define our own types, right? We were talking about this, so let's say we've done that. Okay, so here now we're talking about the null pointer, right? So let's put that on the workbench here, and do we need? Let's go ahead and include. Let's try to run this thing, right? A lot of times these are just sort of theoretical things. Oh. So here we're initializing a pointer to the null pointer, right? And then we're going to say if it's not the null pointer, then do something. But it is the null pointer, right? Now this behaves much the same way. Sorry, what? This second if here, right? You don't have to put the not equal to 0. If you just put null pointer, that's if P naught is a pointer to the null pointer, is a pointer to null, I should say, then that's considered a false statement. And if it's a pointer to anything other than the null, then it's considered true, right? So, this is saying if it's not, this is saying if it is the null pointer, then we're going to consider P naught valid, and that's equivalent to this thing. All right. And what if we put negation here? Then consider P naught yeah. I'm caught in this negation loop. I'm not crazy. So if P naught is false, then not P naught is true. So if P naught is false, which is the case here, then this will be true. So we will execute this loop. So I'm going to see out P naught is the null pointer, which is also, by the way, spelled out this way, right? Okay, so if we run that, P naught is the, yeah, right. So you can see that that did what we thought it would do. Uh-oh, I just closed the wrong thing. Sorry. So I'm going to need to open up that Visual Studio again. Before I go back here, hello, Visual Studio. Okay, let's see. Now, does it find it again? Nay. Nay, it has gone astray. It is wandering about in the woods naked. So properties. Here it is. Okay. Hello. Oh, there. Okay. Maybe I just hadn't turned it on. All right, maybe that's enough to say. I mean, if I wallow in these problems, as I like to do, I like to sit around and experiment with this and that and the other thing, right? So we could initialize it, and then, in fact, let's put this up here. Here I am wallowing about in experimentation land. So I'm going to then initialize it here. So I guess, do I want to, let's have a double D equal to 17.17. And we're going to go down here and say that if it's not, oh, if it's the null pointer, then we're going to say initialize it by giving it the address of D, and then down here we're going to see out dereference P naught and see what it is. All right, now if I execute that, P naught is the null point. Oh, then it says, yeah, dereferencing P naught now gives me, so it's no longer the null pointer. Okay, my point is taken. At least it's made. Okay, and let's get rid of that. exclude from the project and bring in existing item 17.4.5. Here's 17.4.61, which is example code. All right, so maybe we need to read from the text here. The free store deallocation. Right, this is an important idea that you become responsible for memory that you allocate on the free store, or the heap as it is also known. Perhaps, heap kind of gives a connotation of disorganized pile of crap. That's not the right image for the heap. The heap is actually a pretty well-structured tree, I think. Heap is a kind of a data structure that is perhaps misnamed. Why is it called heap? Should we go there? Oh, I don't know what it's complaining about there. Okay. Oh, look, the mathematics of doodling. So I'm going to go here and say C++, why is heap called heap? I don't know, is that a bad way of phrasing the question? There are two different concepts, both called heap. Why are heaps used for memory allocation? Why aren't stacks? Why is heap called so? All right, maybe that's... Who's going to tell us the answer to that? So bytes.com? Bytes.chomsky. That's Noam Chomsky's bytes size website. Sorry. I'm not sure. Okay, so this is a question. It's a forum. I'm not sure if this question is relevant here. Why is heap, the place where dynamic memory allocation occurs, called so? There's also a data structure called heap. What is the connection? All right, now curious minds want to know. Heap contrasts with stack. The latter is a last-in, first-out structure, like a stack of plates. You put new ones on top and pull them off the top. Right. You don't typically reach into a stack and pull out items in the middle. In memory, putting and pulling are allocated and deallocated, are allocating and deallocating. In a heap, you can reach anywhere into the heap to allocate, and you can deallocate in any order, not just in reverse order. You allocate it. Yeah, so there's, so that stack memory and heap memory, those are actually well named then, right? The inventor of the first heap had called a pile or a bag or a shelf. That's what we would go with. So that's one answer. So I'm kind of interested in heap and binary search tree. I know I'm going off on a tangent. A min heap, convert BST to min heap, right? All right, let's just say that these are things you'll learn in data structures class. I just don't like the connotation of heap as being sort of something without structure. That's not a correct way of thinking of it. All right. So the new operator gets memory from the free store. Since a computer's memory is limited, it is usually a good idea to return memory to the free store once we're finished using it. So you can deallocate, right? That way, the free store can reuse that memory for a new allocation. For large programs with long-running programs, such freeing of memory for reuse is essential. For example, consider this, right? And I think this is on our workbench. Each call of calc leaks doubles allocated for P. For example, the call calc 100 1000 will render the space needed for 1000 doubles unusable for the rest of the program. The operator for returning memory to the free store is called delete. We apply delete to a pointer returned by new to make the memory available to the free store for future allocation. Now it becomes, so down here you see we've called calc, which calls or allocates memory on the heap for I guess 1000 here, since we're passing in 1000. Max is 1000. Doubles, that's 8000 bytes. And then we're having a new for res size, so we're allocating 100, and then we're deleting P, which is 1000, and returning res, which is only 100. So this memory is allocated, this memory here. Okay, this is a little tricky, huh? Each call of calcs leaks the doubles allocated for P. Why? Well, so P allocates here, and we're deleting. Oh, this is if you fix that problem, right? So up here we didn't have that delete, right? So here we're deleting it, and then we're returning res. So, you know, we've allocated memory for res. Why did we allocate memory for P? I don't know. It's theoretical, right? It's just for demonstration purposes. It doesn't really have any practical use here. But let's go back to our code and see. Yes, here's this program that allocates memory on the heap, does not free it up, allocates more memory on the heap, and returns a pointer to the second bit, but then completely loses the first bit. And if we well, let's do this. Let's put this in a little loop, right? So I'm going to say while 1, okay, so that's an infinite loop, but I'm going to put a little pause in here. And then I want to sort of look at the memory as we go here. So it's, oh, cin undeclared, did we not? Oh, I guess we didn't. Include standard library facilities. Okay. So I think I want to so it's paused, right? And let's just go take that in there so we can see what's going on. So now I'm in the output window. I'm hitting enter repeatedly, and what do you see is happening? All right, the process memory is growing. Funny, it grows in sort of spurts, doesn't it? And it's in megabytes. But if I don't press enter, it doesn't, right? Because it's sitting there waiting for me to press enter. But yeah, I've already allocated 3 megabytes of memory. And if this were a truly infinite loop, it wouldn't take long for that to then, you know, exhaust what I have available. So it's now on a scale of 7, 8 megabytes. So yeah, let's just leave it at that. All right, so back to here. I'm going to return this to sender and add existing item 17.4.6-2. I believe that's next. And what do we see here? Oh, well, here it's deleting it, right? So this is just fixing that problem. Then notice it's also deleting R. Now, do we need to delete R? What's going to happen if we don't? Well, main is going to end, and when a when heap allocated memory goes out of scope, is it freed? Well, up here, this was going out of scope, right? And yet it wasn't freed. I think here, though, when the program ends, I think you're going to free up any memory. Is it or is it not? Yeah, well, you gotta keep that question in mind as we read on. Okay, so where are we? In a balloon, I know. So there are two forms of delete. You can delete the memory for an individual, or delete with the brackets for an array. It is the programmer's tedious job to do the right version, so deleting an object twice is a bad mistake. So consider here we're allocating memory for an int, which is initialized to 5. We're deleting that int, and then we're deleting it again. P points to memory owned by the free store manager, whereas here P points to an object created by new. So the second delete, you don't own the object pointed to anymore, so the free store manager may have changed its internal data structure in such a way that it can't correctly execute that again. The free store manager may have recycled the memory pointed to by P so that P now points to another object. Deleting the other object owned by some other part of the program will cause errors. All right. Both problems occur in a real program. They are not just theoretical possibilities. All right. So maybe I'll scoot this up here so I don't... Oh, I guess I can't do that, huh? Well, what if I do this and then do this? Oh, that doesn't help, huh? What did I do? I did this, huh? Okay. I just have to know where I am. Where am I? Don't answer that. So 7.5, are we ready for that? Well, I think we have a couple other things to say here, right? Both problems occur in real life. Okay, yeah, so deleting the null pointer doesn't do anything because the null pointer doesn't point to an object. So deleting the null pointer is harmless. Why do we bother with freeing memory? Can't the compiler itself figure out when we don't need a piece of memory anymore and just recycle it without human intervention? It can. That's called automatic garbage collection, or simply garbage collection. I remember putting this on the course outline of record, and the dean at the time, who didn't know any computer science, thought I was having her on. I guess she knows my sense of humor, and figured this was a case of me, trying to put my sense of humor on the official record. Unfortunately, automatic garbage collection is not cost-free and not ideal for all kinds of applications. If you really need automatic garbage collection, you can plug in a garbage collector in your C++ program. Good garbage collectors are available. See, okay. However, in this book, we assume that you have to deal with your own garbage. And we show how to do so. It's Earth Day, so that's a good theme. Deal with your garbage. When is it important not to leak memory? Well, a program that needs to run forever, like an embedded system or something, can't afford memory leaks. An operating system can't afford afford memory leaks. So are most embedded systems, right? Chapter 25. A library should not leak memory because someone might use it as part of the system that shouldn't leak memory. In general, it is simply a good idea not to leak. Loose lips sink ships. Many programmers consider leaks as proof of sloppiness. However, that's slightly overstating the point. When you run a program under the operating system, all memory is automatically returned to the system at the end of the program. So that kind of deals with that question we had here, right? When this program ends, your memory is going to be returned, right? So, all right. You might reasonably then leak memory until the operating system does the deallocation for you. However, if you decide to do that, be sure that your memory consumption estimate is correct, or people will have good reason to consider you sloppy. Destructors. Okay, shall we go put that on the chopping block here? I see. So if I hit F10, my hotkey for, or is it F9? Yeah, F9 also sets a breakpoint, huh? Well, I'll fix that later. I forgot about F9. I fixed F10, my hotkeys. Okay, so where are we? We're back here in code, and we're going to exclude this from the project. And bring in 5. Existing item. 17.5.1, I believe that must be it. There's a -1, and a -2, and a .1 and a .2. Not sure how those are different. Let's see what we got here. Okay, so suppose you've got, and let's build this out here a little bit. Is he talking about the customer here? No. Oh, I'm looking at over here. I don't see no customer. Oh, that's 17.5.1. Okay. Well, let's read this. Okay, so now we know how to store elements to a vector. We simply allocate sufficient space for elements and then store it through the pointer. Okay, so this is for our vector, right? Yeah. So it's got member variable size, a pointer to a double, which is the pointer to the elements, and then the constructor here is the constructor, right? It has initialization list, which says pass the parameter s to the size member variable, and then initialize the pointer to double with, and this is sort of interesting syntax here, right? Maybe, let's see, maybe that's the other one, huh? So let's return this, or let's add, where is it? Add, I don't see add. Add existing item 17-1. If we open that up, we see, yeah, so here's our vector thing, right? So I guess I'll bring this other one back later. Oh, sorry, not looking at that. Seems like the bottom of the text you're highlighting is a bit cut off a bit. Oh, yeah, I know. I need to pay attention to that. Thanks. All right, so here we are in simplified vector of doubles, right? So this is not our template vector, right? There's no way of saying what it's a vector of. It's just hardwired to be a vector of doubles. And our constructor says, oh, notice that the initializer can be parentheses or it can be curly braces. And I think the curly braces say more like construct one of these things, right? So, yeah. So a lem, the pointer to a double, is going to be initialized with the keyword new, right? So we create a vector of s doubles, allocate space on them on the heap, and then assign the pointer to the first of those to the variable named lem, which is a pointer to a double, contains the address of a double. All right, and then we're going to initialize in a for loop, right? So this initializes the elements. We've got size is just a member variable, a member function to return the member variable size. And cleanup, oh, this is going to deallocate, right? Now that should be a destructor, really. So cleanup is not the word we use for that. We're going to show how to build a constructor that does that. But you could have, so down here we have a function f, which allocates n doubles, a function f2, which allocates n ints. Oh, really? Another n? I think it means, right, we're not allocating ints here. Right, so f allocates n doubles, right? We're calling vectors constructor with the parameter size equal to n, which is an integer, right? Size is an integer, and that's going to make n doubles all 0, right? Because of this initializer here. F2 calls the same thing, but it doesn't. I mean, it calls cleanup, right? Which allocates another n ints. I think it means doubles, right? That's a typo there. So different, right? A different vector, right? Because a different scope here. This one is going to be cleaned up, right? So that, in other words, when we leave the scope of this function, it won't be a leak. What do you want to do with v? Well, we could print it out. Do we know how to do that with this? Is not our standard template vector, right? So we'd have to say for int I equals 0, I less than v dot size, and we do have that vector, right? Increment I. Do we have a way of allocating? Yeah, I think we can just say cout v dot. Do we have access to? Oh, maybe we don't, huh? Yeah, these are private variables up here. So if you want to get access to the elements of this vector, you got to provide a facility for that, right? We have a way of initializing them in here, but we have no way of returning them. So let's create a member function here, which is going to return a double. Get a lem. It's going to take an int I, and in the body here, we're going to return a lem of I. That ought to work, huh? So now we have a way of getting it, and let's then call that on I, and let's go ahead with it. I think maybe we don't have our standard template. We don't have any libraries at all here, right? But we don't want to use the vector library because, that might cause, probably wouldn't, right? Because that's a template. But let's just include what we need. All right. So now it doesn't complain about cout. And then when we clean up, okay, so f, again, f is going to allocate how many? N, right? So we're calling f with 5. So let's say we call f with 50,000, and we do these in a loop. So for int I equals 0 or something like this, I less than 100, I don't know, or let's say 20, increment I, and do that in a loop so we can see the memory leak. And then we'll do the same thing for this guy, and then we won't see the memory leak. Will that convince everybody? I don't think you need convincing. I don't know why I'm... See, this is why it takes so long, because I can't help but experiment with these things, which I encourage you to do the same thing. All right, so if I compile this thing, does it run? Yes. And there's the code. Oh, what, it's still running the other one? What? Oh, it must have gotten confused about which one is which. So how do you recover from that? Well, maybe it's because I still had the output window open. So let me try this again. If I say F5. Oh, F5 with this focus. Okay. So there you see all those zeros, right? So that's a lot of zeros. Oh. Oh, I should have put a pause in there, right? Yeah, I guess the same thing here, huh? Okay, so is it waiting for me? And I think maybe we want to go back to the code window. So I'm just going to be pressing. So let's see. I want to again see the memory being the process memory here. So as I hit enter, you see it's jumping up, right? That's 5, 6, 7, 8, 9, 10, 11, 12, 13, 14, 15, 16, 17, 18, 19, 20. Okay. Now in the output window I have 7 zeros for some reason. But notice that, yeah, so I'm getting a sequence of, you know, if you go back, you can see that I'm getting these zeros, right, as I press enter. It's not increasing the memory allocated. It's still like 9 megabytes, but the other memory that was allocated, that was leaked away, didn't come back, right? Just because that for loop went out of scope and F went out of scope, we didn't recover that memory. Okay, good enough. If you have questions about that, just chime in. Okay, so we've got exclude this from the project. Okay, do we have a second one of these? Oh, add existing item. I guess we'll go to 17.5-2. I don't know, 17.5-2. Oh, that's .2. Here's -2. So what's going on here? Here's our oh, okay, so here we have the destructor, and I don't know, is this something, a lot of you probably know this already. That's how you define a destructor. So a constructor is a function with no return type and the same name as the class. So up here we have our constructor. A destructor just has a little tilde. It's like a negation operator on the outside. That's the way you think of it. And it's got a body here. You see the body? And in that body, we just delete the heap allocated memory there. Okay, and then we have a third function here, F3. Oh, yeah. And F3 allocates memory for an array of n ints. We call vector of, we construct a vector of n, which is passed in. We delete that vector. So we could use P and V together here. So what's the point here? Is this a memory leak? We're deleting P. are we going to be leaking the memory for V? Because we're not calling V's destructor, right? Well, because we provided a destructor, when the variable goes out, when the variable V here goes out of scope, its destructor is called. So let's see if that isn't true. I think that's what he's going to be on about here, right? So this is this very simplified vector of doubles. One of the most common problems with the free store is that people forget to delete. It's a hoarding thing, right? I'll just keep that for later. No, you don't have access to it anymore. You've lost, the pointer to it, and yet it's still allocated. So the equivalent problem would arise for cleanup. People would forget to call it. We can do better than that. The basic idea is to have the compiler know about a function that does the opposite of constructor, just as it knows about the constructor, right? So there's a default constructor, there's a constructor. This is not the default constructor, but inevitably such a function is called a destructor, in the same way that a constructor is implicitly called when the object class is created. The destructor is implicitly called when the object goes out of scope. So this will not be a problem here then, right? Because V has a destructor now defined, right? It's these two lines of code here, right? And so when this vector goes out of scope, it won't leak memory. I suppose we could, do repeated calls and see that the shall I pull this out here? See that the memory is not leaking. Okay. All right. So let's go. So what is this next business here? Generated destructors. Well, let's see. We haven't finished talking about this, right? So here's an example. Suddenly, the delete looks rather tedious and error-prone. Given vector, there's no reason to allocate memory using new just to deallocate it using delete at the bottom of the function. That's what the vector does and does better. In particular, vector cannot forget to call its destructor to deallocate memory used for the elements. Great. So we are not going to go into great detail about the uses of destructors here, but they are great for handling resources that we need to first acquire from somewhere and later give back. Files, threads, locks. Remember how IOStream clean up after themselves? Do they? They flush buffers, close files, free buffer space, etc. Yeah, that's described in chapters 10 and 11. That's done by their destructors. Every class that owns a resource needs a destructor. Yeah, owning means you allocated it on the heap. That means you're responsible for it. You own it. And that's why you should write a destructor for your classes that allocate heap memory. Okay, so generated destructors. If a member of a class has a destructor, then the destructor will be called when the object containing the member is destroyed. So here we've got a structure customer with a name and a vector of strings called addresses. And then there's some function that creates a customer. And when you exit that function, so that Fred goes out of scope, Fred is destroyed. Well, we didn't create a destructor for Fred, did we? Well, vector allocates memory, but vector has a destructor, right? So that when you exit this function where customer was created, vector's destructor is called, and you don't have to, you're not responsible for it, right? So that's the whole idea of these containers, is they handle that for you. This is obviously necessary for destructors to be useful and is sometimes expressed as the compiler-generated constructor for customer, which calls the members destructors. The compiler generated a destructor for customer, which calls the members destructors. Okay, that is indeed how often the obvious and necessary guarantee that destructors are called is implemented. Okay, so destructors for members and for bases are implicitly called from a derived class destructor, whether user-defined or generated. Basically, the rules add up to destructors are called when the object is destroyed by going out of scope, using delete, etc. Okay, so destructors in the free store. Destructors are conceptually simple, but they are the foundation for many of the most effective C++ programming techniques. Basic idea is simple. Whatever resource a class object needs to function, it acquires in a constructor. During the object's lifetime, it may release resources and acquire new ones. At the end of the lifetime, the destructor releases all resources still owned by the object. The matched constructor-destructor pair handling free store memory for vector is the archetypical example. We'll go back to the idea with more examples in Chapter 19 if we ever get there. Here, we will examine an important application that comes from the use of free store and class hierarchies in combination. So consider here, we've got, this is a little bit tricky because it's using the full tick library. So if you have a function that returns a pointer to a shape object, right, where a shape is a virtual class, so that you have to override its draw function. But this is then going to okay, so we have a text shape. And so TT is a text object, and it has to know where it's going to exist and what its text element is. And then we declare P to be a pointer to a shape, P is a pointer to a shape object. It's allocating this text on the heap, and we're returning P. So P is then assigned to Q here, right, which is a pointer to a shape, so it's the right kind of object, and then we delete Q. This looks fairly plausible, and it is. It all works, but let's see how, because that exposes an elegant, important, and simple technique. Inside the function FCT, the text object TT is properly destroyed at the exit from function, right, because it goes out of scope. Right, that's a particular kind of object, and it has a destructor. When it goes out of scope, it's destroyed. Text has a string member, which obviously needs to have its destructor called. String handles its memory acquisition and releases it exactly like vector. Right, so string has a destructor. For this text object TT, that's easy. The compiler just calls text-generated destructor as described in section 5 previously. But what about the text object that was returned from function? The calling, so we're calling, somebody calling f is going to call function. So the calling function f has no idea that q points to a text. All it knows is that it points to a shape. Then how does delete q get to call text destructor right here? Right, so text destructor. So all f knows is that q points to some kind of shape. It doesn't know what kind of shape. It turns out it's a text shape. So how do we know to delete a text? Well, in chapter 14, we breezed past the fact that shape has a destructor. In fact, shape has a virtual destructor. That's the key. When we say delete Q, delete looks at Q's type to see if it needs to call a destructor. If so, it calls it. So delete Q calls shape's destructor, but shape is virtual. So using the virtual call mechanism, that call invokes the destructor of shape's derived class. Had shape not been virtual, this would not have been called. The destructor would not have been called, and text string member would not have been properly destroyed. We'd have a leak. So the rule of thumb: if you have a class with a virtual function, it needs a virtual destructor. The reason is, if a class has a virtual function, it is likely to be used as a base class, and if it is a base class and its derived class is likely to be allocated using new, and if a derived class object is allocated using new and manipulated through a pointer to its base, then it is likely to be deleted through a pointer to its base. Okay, so try this. Write a little program using base classes and members where you define. Okay, so let's go ahead and copy this to our clipboard so we can paste it into our little try this. Okay, so we're going to go to here and see that we can get rid of this, exclude this from the project, and add a new item. Not new project. Oh crap. We can just, okay, I clicked on the wrong thing. Add new item. So I'm going to say this is PPP17 try this 01. Okay. Oh. Already exists on the disks. Oh, really? Have I already done this? Let's see. So I'm going to let's just bring it in then, since it's already here and we're short on time. So add existing item. Do I have that? It's funny. I would give it exactly the same name. Huh? There it is. This is dated 4/20. Oh, did we already do this? Oh, maybe I did it. I forgot I did it. Oh yeah. Yeah. It's all coming back to me now. Seems like I've been here before. Well, it bears revisiting. Okay, so we did the size of, maybe this is the second one, huh? That was the first one? Okay, sorry, this is not the first try this. This is the second try this. So let us now praise memory. Exclude from the project? Okay. So add new item. Okay, so I'm going to say, that's why I gave it a number, right? PPP17. Try this 02. Toto 2? Yeah, alright. So, do I still have that on the clipboard? This is me. Oh no. Write a little program using the base classes and members you defined. Little program using base classes and members where you define the constructors and destructors to output a line of information when they are called. Then create a few objects and see how the constructors and destructors are called. All right. Okay. So we're going to include the usual suspects, or should we use standard library facilities? Include standard library facilities. Okay. And then we want to create a class. What do you want to call it? Well, this is just abstract, right? So we can call it whatever you like. Just don't call it late for, late for lunch. It's different than out to lunch. Okay. And it's going to have a public section. We need to say public because by default it would be private, right? And we're going to say we've got a constructor. What shall it say? How about something like, you know, announce who we are. So cout, I'm late for lunch. Okay. And then how about a destructor? And we're just going to say, oh, sorry, yeah, I'm giving it the wrong name, aren't I? I was thinking I was going to call it A. Okay, so this is going to be late for lunch, and it's going to say, I am the destructor. Late for lunch, destroyed. Okay, is that going to do? Okay, so there we have a class. It's not a virtual, it's not a pure class, right? Do we want a pure class? Well, I think the idea here was not necessarily... Can I bring this over here? New line information when they are called. Then create a few objects to see how their constructors and destructors are called. Okay. So should we have another one? What do you want to call this one? Late for dinner? And it's the constructor, right? So maybe we should emphasize that it's it's a function, and that yeah, well, that's all right. Late for dinner destroyed. How are we doing? All right. Oh, late for dinner. Okay. So then we're going to have a third class, early to rise. And it's going to create a class with a capital C. No, not with a capital C. So we're going to have this is going to call it's going to have a couple elements, right? So let's create a late for lunch object. Can we call that A? And let's call, so these are private member variables. Is that what, yeah, sure. Okay, and then we're going to have late for dinner. Let's make that B, and then we'll have a way of creating an early to rise object. So that's the early to rise constructor. And what's it going to do? Anything? Well, let's do the same thing, right? It's going to say see out early to rise. And should we have a destructor for that? Do we need a destructor for that? Yeah, all right. That's the whole idea, is that these guys need to provide their destructors. Oh, wrong character there. It's close, but no cigar. Okay, so there we go. Early to rise destroyed. Any more of these you want to do, or highlighting? Yeah, okay, that's fine. Let's say that's good. So we'll have a function, a little void function that creates objects of these types. So we announce that we're in here. See out in function. Should we be having? We should be having little end lines on each of these. Otherwise, they're all going to run together, right? I put a \n here. Just copy and paste those throughout. Not there. Why is that there? I don't know. Oh, okay, then I don't need this, huh? Okay, and then I'm going to create an object of type late for lunch. Do we need the constructor? No. Okay, so then late for dinner. LD. So we have an early to rise. ER. And then we're out of there, right? So let's say that we're leaving function, because what's going to happen when we leave function? Oh, sorry, we're out of scope here, huh? What's going to happen when we leave function is that all the destructors are going to be called, right? So we should see that after. So when we construct these things, we'll see that they're built, and when we leave them, we'll see that they're destroyed. So here's main to drive that, and I think all we need to do is call function. It doesn't like the fact that function is a void function. What's oh, we got an extra. No. Oh, this is missing its semicolon, huh? Oh no, that's a function. Okay, so this is missing its semicolon, huh? Okay. All right. So. All right, let's be done with it. Okay, so F5, it compiles first time every time. Oh. Okay. So what do we see? So in function we create these three things, right? And each one of their constructors is called, and you can see that they say who they are and that they are created. And then in the order they were created, so shall they be destroyed. Oh, in reverse order. So the last one created is the first one destroyed. So yeah, that's because there must be like, that's the call stack, right? I suppose you could see that if you wanted to look at the call stack. Do I have access to the call stack here? Yeah, it just says it's on line 41, which means it's done, right? Okay. Okay. Any questions about that? I think we kind of covered that. All right. Okay, so I can post that in the chat for today, or in the discussion. Don't confuse your discussions with chats. Those are distinct things. Okay. And oh, notice that it's not done yet, right? Okay. All right. So where does that bring us to? I got about 10 minutes to break. So what's our prognosis here? 17.6. Oh, we got like a lot to go. Oh my God. All right. So access to elements. We kind of talked about that already. All we did is create a get function, right? So let's move on. Pointers to class objects. The notion of a pointer is general, so we can point to just about anything we can place in memory. We could have pointers to vectors, exactly as we have pointers to characters. And that's a way of sort of saying I have an array of vectors, right? And we can allocate memory. Oh, sorry, you're not looking at that, are you? We can allocate memory on the heap for an array of vectors, for S vectors, say. So 17.7, shall we put that on the clipboard? Remove this, or no, not remove, but exclude it, and then add new or existing item, namely 17.7. And is this what we think it's going to be? Yeah. So F takes an integer and returns a pointer to a vector, which is going to be the first among a set of S vectors, right? So that's like a matrix, essentially, right? Each vector is like a row, and then the array of rows is a matrix. Notice that we're not destroying V because we're returning a pointer. Oh, yeah, so we say that we're going to copy that. What are we copying? So V is a vector, right? And we've allocated memory for vectors, right? And so yeah, you might say, well, vectors destructor will destroy that. No, because we didn't allocate memory for a vector. We allocated memory for an array of vectors, right? So maybe V goes out of scope, but V has been assigned to the contents of P. So we've initialized our pointer by having it point to a vector, the first of many, right? Okay, so that's what F does. What does FF do? Well, it creates a vector, an array of vectors. Oh, yeah, so it calls F, huh? So it's F returns a pointer to a vector, and this in case will memory has been allocated for an array of 4 vectors. How big are those vectors? Well, each vector is of size 4. And so this is like a 4 by 4 matrix, huh? And then we dereference Q, which is now a matrix, and assign that to a vector VV, and then we're going to delete Q, and we're done, huh? So that little dot 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 there means maybe we did something with that, but it's all going to disappear. All right, we freed up the memory for Q, which was our matrix, or 4x4 matrix, right? So shall we print out that matrix? Do we have the get function for our? Yeah, right. So we have a little get function for reading. So we could in this dot 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 space here. Do we? Yeah, we included vector. Oh, that's odd, isn't it? Because we're defining our own vector. So how does it know which vector to use here? Well, we're not actually ever using the template vector, right? So we don't need that. It seems a little odd to be including vector here. Should we just comment that out? But let's say we do want to include IO stream, and using namespace standard. So in this little dot 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 here, then we want to see what's it? Are these going to be zeros? They're going to be all zeros, aren't they? So for every vector v, I don't know if the range base for loop is going to work, right? So how do we allocate, how do we access elements of this matrix? I think we have to use the nested dot operators. So for int I equals 0, I less than so P. Oh, sorry. Well, this is the first F, right? So okay. So we're in here with just a one-dimensional vector, right? I was thinking I was down here. Oh, down there, right? But we're up here. So this is just a one-dimensional vector. So we can say v dot size, right? There's such a thing. Increment I, and see out v dot get of I followed by end line. Okay. Shall we just do that much for now? Let's see if that compiles. No, we got a problem. Vector is not a member of std. Oh, so down here in main, what's it doing? Yeah, vector's not a member of std. You can't do that. This is an example with standard STL vector. Okay, so it's saying, yeah, so notice that here is the template, right? Okay. All right, we can put this back in then. Sorry, I didn't realize that's where that was happening. All right, so now down here, yeah, these are all now recognized. This vector, so you'd think that this maybe is going to be some kind of variable collision, right? Because we're using the same name. One is a template type and one is not. The one we created is not, right? The standard template library is a template type. How are we doing? We're coming up on the break here. So what's the problem down here? All classes support the dot operator for accessing members. But it doesn't like, what does it say here? Ambiguous. Yeah, we got variable collision. So can we do this? Yeah, I think maybe we need to, right? Just give it a different name. This is going to be a little tedious here, sorry. Oh, and then where am I? Here? Okay, so this is the FF function. Okay. So anywhere I don't have a template vector, I want to use just vector without the R. Then down here I am using standard vector. And I'm using, I don't need this, right? Because I'm using the namespace standard. So here P is a pointer to a vector of vectors. We're allocating enough memory for 10 of these. And then we're deleting P. We didn't do anything with it, right? This just proved that you could do that. Okay, then down here we're going to go back to our other vector. Oh, you can't see that. I think, yeah, I think we're all good now. Shall we try to compile this? And action. Camera. Oh no, we got error. Okay, so this is, I forgot to delete the O in this one. F5. Action. So I don't see the output. It disappeared. Let me try that again. Oh. It disappears. F5. If I go to output here, yeah, it's just my hotkey isn't working for some reason. So it doesn't show anything. There's no output. All right, so maybe that's why I just exited, right? I thought I had put in a little printout thing here, and that was in F. Yeah. What happened to this? Do we get to F? Who calls F? Nobody. So it's a theoretical thing. So let's see. Does F doesn't take any input? Oh, it takes an integer. Oh, FF is what? Yeah. So nobody calls FF. FF calls F, but nobody called FF. Where should we do that? Down here, maybe? I don't know. Okay. So now let's compile and run that. And triggered a breakpoint. I didn't want a breakpoint. We got a disassembly thing going on here. Why do we have a breakpoint? I don't see a breakpoint here, so it triggered one somehow. Yeah, so we're deep into the weeds here. Shall we call this earlier on, maybe? So as soon as we get into main, how about we just call FF? And then we'll call a little pause here. Oh, I've got access error. So at FF is allocating memory for Q. Yeah, it's calling F on 4, right? And when you call F, so how about we put a little cin.get here, so we just don't go beyond that point until. Oh, I need to stop this and then compile and run again. Okay. So we've got garbage value. Oh, you can't see those. Yeah. We've got garbage value. So there's our vector with 4 elements. They're supposed to be zeros, I think. So why aren't they zeros? I will allow you to ponder that. You probably have that as a question, or maybe you can answer that question. I will pause for answers or questions. It's A and Q time. Or we can just take a break and think about that during the break. Okay. I'll put back the code, right? So the code that produced that garbage is right here, right? So v.get of I. So we have allocated memory for a vector v. Oh, maybe we need to put this after. Okay, sorry. So v got created here, right? With s elements, or 4 elements. And the constructor for a v, oh, it doesn't have the initializer. That would answer that, huh? So we allocate memory, but so the constructor doesn't do that thing that it was doing before, right? So we're going to say for int I equals 0, I less than size, increment I, and say a lem of I equals 0.0. Okay, so now when we run this thing, there they are. May the 4 zeros be with you. So the standard vector is an array that rebuilds itself every time you change it, right? Not necessarily. I mean, what do you mean by changing it? So if you were to push back, it would only need to rebuild itself if... Yeah, see, we're going to get to this, right? There's something called the capacity, which is different than the size. And the capacity is generally larger than the size. But if the size gets to be as large as the capacity and you push back, then yes, it does rebuild itself in memory, and we're going to talk about how that happens. So when you change the size, right. Yeah, good point. That's exactly where we're going. Okay, folks, take 10. I will pause the thing here. Yikes. And here. All right, so starting to get the hang of how this vector thing is a little bit tricky. Yeah. Right. And so we were okay. So now the next thing was to in FF, maybe can we get I think we can just call the dot operator on the dot operator. Dot's nice. All right. Yeah. So yeah, for int I equals 0, I less than. So what have we got here? Now we got VV. And then inside VV we have V's. Now a V is actually a Q. Q is a pointer to a vector of 4 elements, right? So we're going to say for int j equals 0, j less than vv dot get of I dot, that's going to be a vector, right? So it's going to have a size. It doesn't like that. So now Q is a pointer to a thing. So VV contains the contents of Q. And Q is a vector of 4 elements. So VV is just a copy. Okay, so maybe it's not a vector. I mean, not a matrix. I was thinking matrix here, but can we then say Q? We could use the arrow operator. Have we talked about that? And and let's see. Yeah, there's a lot of different ways of doing the same thing here, right? So this is not required, the way of doing this. So yeah, I was wrong about what that is, huh? Okay. I'm just using the arrow operator because I don't want to dereference and then use the dot operator with parentheses. So maybe I'll make a comment here. Exactly the same as if I were to dereference Q in parentheses and then use the dot operator. So why the parentheses? Well, the dot operator takes precedence over the dereference operator. So if you want to dereference first and then dot, you have to put it in parentheses, which is an awkward notation. Thus, we have the arrow operator. Let's see if it works. So if I compile, does it even compile? Yeah, it compiles. And it's waiting for enter. Okay, and now these are not, I've got now triggered a breakpoint. That was a breakpoint we were getting before, right? And these have not been initialized, right? So they have garbage values. Maybe I'll note those, right? Oh, whoops! I'm going to go here and that's not there. That's over here. And yeah, we kind of crashed on this puppy, so let's go back to here, and I'm just going to paste this in, and we'll just move on. But you know, I'll post this up later, and so maybe I'll make a question here. So F was or V was initialized, but the copy of V through the pointer did not copy elements. All right, so I can kind of see that here, right? Okay, let's just leave that well enough. I think we learned what we need to learn there. We can move on. So I'm going to save that. Go to the Solution Explorer. That was 17.7, excluded from the project. Go to Add a new item. Oh, no, not a new item. Damn it. Add an existing item. 17.8. I think there's only one of those. Let's see what it looks like. See what we're getting into here. So this is not vector anymore. We're back to sort of talking about messaging. Oh, yeah, here's a void star. Okay. With some static cast action here. And I think this is something we talked about before, so maybe we don't have to belabor it too much. But let's see what he says about it, because I think it's important stuff. So this is 17.8, messing with the void star. Patrick, what's his name? Patrick Jacobs, I think. Yeah, that's his handle. Who you may know from Mesa, or I think he's transferring to UC or CSU Channel Islands. At least that's the plan. I don't know. Y'all, anybody transferring in here? Things are weird out there, I got to say. There's rumors which I hesitate to repeat, but I did hear a rumor which I could not verify about one UC already declaring that fall was online. I don't know. What do I know? I have opined that I don't like that. Apparently I don't have to like it. You hear so many different things. I heard that the Israelis had colonized the moon and they're going to leave us behind. Yeah, pass that on. Right. Okay. So anyway, right. So we're reading 17.8. Using pointers and free store allocated arrays, we are very close to the hardware. Basically, our operations on pointers, what do we have so far? Initialization, assignment, dereferencing, and subscripting, indexing, map directly to machine instructions. Yeah, we could look at the assembly code, right? At this level, the language offers only a bit of notational convenience for the compile time consistency offered by the type system. Occasionally, the type system meaning, strongly typed objects. Occasionally, we have to give up even that last bit of protection. Naturally, we don't want to make do without protection of the type system. But sometimes there is no logical alternative. For example, if you have to interact with another language that doesn't know about C++'s types. Yeah. Python comes to mind. There's Cython. What is it? Yeah, Cython, I think it's called. Which is like Python interacting with C. There are also unfortunate number of cases where we need to interface with old code, legacyware, that wasn't designed with static type safety in mind. For that, we need two things: a type of pointer that points to memory without knowing what kind of objects reside in that memory, and an operation to tell the compiler what kind of type to assume without proof for memory pointed to by one of those pointers. What type to assume? Okay. So void star means pointer to some memory that the compiler doesn't know the type of. We use void star when we want to transmit an address between pieces of code that really don't know each other's types. For example, the address of arguments of the callback function. Oh, we kind of skipped that, didn't we? Yeah, that's sort of in, it's kind of that infinite loop that we see in the SFML game loop. And the lowest level of memory allocators, such as implementation of the new operation. Yeah, how is the new operator written? Using malloc, short for memory allocation. There are no objects of type void, but as we have seen, we use void to mean no value returned, right? So you can't declare an object of type void, but you can say that a function doesn't return anything. Right? So that's what those two things are. A pointer to any object type can be assigned to a void star. For example, we can say I'm going to allocate memory on the heap for an int and assign its address to PV1. And PV1 is a pointer to... Huh? Yeah. It doesn't have a type, right? So this is this void star thing. You can also make a vector of those, right? Since the compiler doesn't know what void star points to, what type it points to, we must tell it. Okay. So are we seeing this over here in this code? So here we have, yeah, you can't do this. We just talked about that. So that's what he was saying. Then main has two allocators, one to an int and one to an array of doubles. They're okay, it says here. And then we have a function that takes a pointer to void, and you can copy a pointer to void to another pointer. But you can't copy a pointer to void to a pointer to double. Right? Why not? Well, a static cast can be used explicitly to convert between related pointer types, such as void star and double, pointer to double. Okay, so, but this is not allowed, right? Directly, right? But so what do? Well, you static cast your pointer to void to make it an explicit conversion. So here we're converting a pointer to void to a pointer to int, and then assigning that to a pointer to int. So we could also do that here, right? So back over here, yeah, we see that that's what's going on, right? Cannot dereference a void. So yeah, don't try to dereference a pointer to void and assign that some value. C++ will complain. We don't know what type it points to. We can't use the subscript operator and assign it that way. It's the same as this, right? It's the same basic thing. In fact, we could do this. Well, here's an issue, right? Pointer arithmetic. Sorry. So this operation is exactly the same as this operation, right? So you're adding 2 to the pointer, but to add 2 to the pointer, you have to know what kind of thing it points to, so it knows what kind of memory offset to give, right? I think, can you even do pointer arithmetic with a void star? I don't know. I don't know as I've tried that. I guess the sensible interpretation of that would be, you know, add bytes, add 2 bytes, right? Because that's the smallest addressable unit of memory. But you certainly can't do this, so you probably can't do this. Yeah, right. You can't do this either, but yeah. All right. But here, this is the way you do that, right? And so the cast here does not mean cast a spell. It means, you know, make a plaster cast and fix this broken bone. Or that's the metaphor. So and none of these things are used here, our main program here. So you're really not meant to run this thing. But these things are okay, right? They're saying you can create a single pointer to void and initialize it with an int. So then it'll point to the first byte of that int, but it won't know that it's an int. Right? So let's try to see what happens here. I think we kind of played with this before, but it bears repeating. So I'm going to say I've got an int, I've got an int I equal to 17, and can I, okay, I guess here, how about this? If I initialize this to 17 that way, right? So I guess that's kind of what I was intending to do with that. And then if can I dereference? I don't think can you do this? well, first of all, we don't have our stream library. Still doesn't like it, right? Oh, yeah, sorry. Using namespace standard. Okay. So yeah, this it doesn't like. This PV is PV1. Yeah, now it doesn't like it because it says okay. Pointer to int converts to pointer to void. This expression must be a pointer. You can't see the little dialog box I'm reading, I know. But I'm hovering my cursor over this thing, and it says expression must be a pointer to a complete object type. Yeah. So can I do a static cast on that? So pointer to static. Whoops. Cast, and let's cast it as a pointer to int. Still doesn't like it. Oh, sorry, yeah, it doesn't. That's the wrong syntax. Okay, so it still doesn't like this, right? Expected a parenthesis? Oh, yeah, okay. Sorry, syntax error. Right, so that is okay. And if I run this thing now, do I see 17? Yes. You're not seeing it? Oh, it went away for some reason. I think because I pressed enter with it in scope. So if I say F5 and then more quickly skip over to... No, that didn't work. Okay, I'm here. F5, compile and run. Oh, darn it, the wrong thing. Try that one more time. Oh, focus over here. F5. Oh no. Okay, so I guess if I put a little pause here. There, 17, right? But what if I were to cast it as something else? Like a character. Can I do that even? And what would we get? Yeah, we got a character, a little box. See it there? A little box character. And where is that in the ASCII code? And why does 17 give us that? I think that maybe, so 17, if you were to write 17 as a byte, it would be, 16 plus 1, so what, 10001, something like that. Is that, so if we go to the ASCII table, where do we see, can I get to the ASCII table here? What am I looking at? Sure, let's go ASCII. All right. I don't know. I didn't want a picture of the ASCII tables. Come on, Google. You know what I want. Okay, so 17. Yeah, so that's a special character. So maybe should we try something else where? How about 65? Right. So if we go back to our code here, and we say, yeah, make this 65. Will we get an A? I don't think so. F5. Oh yeah, sorry. It all depends on whether, is that the least significant byte or not, right? And so, oh yeah, so you see the A there? Right, so we static cast, so even though we define it to be an int, when we static cast it as a character, right? Okay, so that's fine. All right, maybe we need to leave this thing. Yeah, get through with chapter 17. Okay, so uh, add existing item 17 point. Oh, there's an 8.1. What's that? Oh, okay. All right, let's go and read about that. How are we doing? It's 412, which was 10 days ago. 411 was the passing of John Conway. It's one of those dates. Let's see. So, what do they say here? So the reinterpret cast. So we kind of see castaway const, right? Oh, well, no, we haven't talked about that. Okay. All right. So a static cast can be used to explicitly convert between pointer types such as void star and double pointer. The name static cast is deliberately ugly for an ugly and dangerous thing. Use only when necessary. Break glass before you use this. You shouldn't find it necessary very often, if at all. An operation such as static cast is called an explicit type conversion because that's what it does. Yeah. Even nastier than static cast is reinterpret cast, which can cast between two unrelated types such as int and double. Const cast can cast away const, which sometimes sometimes you actually want to do that. The whole const thing can be annoying. So, for example, and this is, I think, oh, that was actually in the last code that we were looking at. So here, the first example, classical, necessary, and proper use of reinterpret cast. That's this one. We tell the compiler that at a certain part of memory, the memory starting with location here, is to be considered a register, presumably with special semantics. Such code is necessary when you write things like device drivers. So you want to say, this is our entry point, and from there we're going to go somewhere else. We're not going to do much of that, but keep that in mind for future reference, I guess. In the second example, the const cast strips away the const from the const buffer pointer called P. Presumably, we know what we're doing. At least static cast can't mess with the pointer integer distinction or with constness, so we prefer static cast if you feel the need for a cast. When you think you need a cast, reminder or consider, is there a way to write the code without that cast? Is there a way to redesign any part of the program so that the cast is not needed? Unless you are interfacing to other people's code or to hardware, there's usually a way. If not, expect subtle and nasty bugs. Don't expect to use reinterpret cast to be portable. Oh, yeah, don't expect using that to be. Okay, 17.9. Okay, I think this code here must have been from the previous text. Oh, what am I talking about? This code here. From the previous edition of this text, and because it's not used here. So let's just, in the interest of, oh, that was 9, huh? Sorry. This is 9.1. Okay, so we're in section 9. Okay, great. Which means that we're almost at the end. We can get to the drill if we, I don't know. Well, let's see. So, pointers and references. Okay, so we're back to here. And if you can think of a reference as an automatically dereference immutable pointer, you can think of a reference as an automatically dereferenced immutable pointer. All right, this is a little tough to get used to. or as an alternative name for an object, an alias for that object. Pointers and references differ in these ways. And this is, some important principles here. Assignment to a pointer changes the pointer's value, not the pointed to value. To get a pointer, you generally need to use new or ampersand, right? That's the way we get an address. To access an object pointed to, you dereference or index, or subscript. Assignment to a reference changes the value of the object referred to, not the reference itself. You cannot make a reference refer to a different object after initialization. That's the immutable part, right? Assignment to references does deep copy, assigns to the reference to object. Assignments of pointers does not. Assignment of pointers, does not. It assigns to the pointer object itself. Beware of no pointers. Yeah, that's always true. So for example, so here we have a variable x of type int initialized to 10. We create a pointer to the address of that object. We assign 7 to that address. Right, so assignment to the reference. Right, okay. So we can assign to that dereferenced location. Here x2 is a variable of type int, which contains the contents of 7, right? The contents of what p is pointing to, which is 7. And p2 is assigned the address of x2, which is then a variable of type pointer to int. So you can get a pointer to another int, and we can assign a pointer to a pointer, no problem. You can make a pointer point to another object. So the corresponding example for references is we have a variable y of type int, and r here is a int reference, and it's in the type, not in the initializer. Right? So what is r? R is essentially just another name for y. So r is for reference here. So why have another name for y? I don't know. Sometimes it's useful. We'll see. So can we assign 7 to r? Yeah. We can change the value of that reference so that it's the reference itself is, so you're actually changing y here, right? You're changing y to be 7 as well, right? So then we can read y through r. So r is going to contain the value 7, and we can assign that to y2. We can assign y2 to r2, which is another reference. We can assign a reference to a reference, but you can't assign another address to a reference. So you might think, well, this is a reference too. Well, that's see, r is just another name for y, right? Because of what we did here, right? And so here we're just it's like assigning y to r2, which is like assigning 7 to r, right? You're just assigning a value to that. Yeah. So in that last, it's not just this construct that will fail right here. You can't change the value of a reference. So by assigning another reference that way. So you might say, well, R is a reference, and R2 is a reference. And so aren't we assigning a reference to a reference here? Well, yeah, essentially R is another name for Y. And so it's like assigning Y to R2, which will, Y is currently 7, I believe. So I suppose we should fiddle with that a little bit. But time is short, so let's move on. There is no way to get a reference to refer to a different object after initialization. If you need to point to something different, use a pointer. So a reference and a pointer both implemented by using a memory address. They just use that address differently to provide you, the program, with slightly different facilities. Okay, 9.1. When you want to change the value of a variable to a value computed by a function, you have three choices. And those are described here. So we want to, so we have increment v, a function that takes an integer x, and it's going to, increment value, right? So the value that it takes in is incremented by 1, and we return that to whatever function calls it. Or we could increment the pointer. So we take a pointer and then we dereference the pointer and increment that. And that will change the value of the thing pointed to by p, right? So that's like passing by reference. And this is also passing by reference, right? So how do you choose? Well, we think returning the value often leads to the most obvious and therefore the least error-prone code. So that is that if you were to have an integer, a variable type integer x initialized to 2, and you were to pass it into x and then assign that to x, then x would be 3. And that's pretty obvious what's going on, right? We prefer that style for small objects such as int. In addition, if a large object has a move constructor, oh, well, that's coming up in chapter 18. Yeah, hang on for that. We can officially pass it back and forth. So we get our first dive into the idea of move semantics. How do we choose between using a reference argument and using a pointer argument? Unfortunately, either way has both attractions and problems, so again the answer is less than clear-cut. You have to make a decision based on the individual function and its likely uses. Using a pointer argument alerts the programmer that something might be changed. It's like passing by reference. You're saying, yeah, I might change this thing, right? Here we need to pass by reference if we're going to increment the pointer, right? Or increment through the pointer, right? We're not incrementing the pointer, we're dereferencing the object passed in, which is the address of x, and then incrementing what's at that address, which actually deals directly with that bit of memory, right? So that'll do it, right? So, you know, this seems more obvious up here, but this does the same thing. It's a judgment call. You can also just do increment the reference, right? Which is here, right? The need to use the reference in increment by pointer or through the pointer alerts the user that x might have changed. In contrast, increment the reference looks innocent. This leads to a slight preference for the pointer version. A warning, on the other hand, if you use a pointer as a function argument, the function has to be aware that it might call it with a null pointer. So what happens if you call increment pointer with a null pointer? Crash. Bang, boom. Same thing here, right? So we've declared p to be a pointer to int, but it's assigned the null pointer. This is obviously nasty. The person who writes increment p or through p can protect against this, right? So if null pointer, throw an error. Okay. But now increment through pointers suddenly doesn't look as simple and attractive as before. Yeah. If passing nothing, passing no object is acceptable from the point of view of the semantics of the function, we must prefer the pointer argument. That's not the case for the increment operation, hence the need for throwing an exception with the null pointer being passed in. So the real answer is the choice depends upon the nature of the function. For tiny objects, prefer pass by value. For functions where no object represented by null pointer is a valid argument, use pointer. Use a pointer parameter and remember to test for null pointer. Otherwise, use a reference parameter. And then, yeah, the weird thing about passing in a reference is that it becomes actually both input and output, right? Because when you change it, that's the output of the function essentially, right? The effect of the function is to act on the input without actually, having an explicit return thing that shows that. Pointers, references, and inheritance. Okay, well, we're getting short on time here. Yeah, we didn't get to the second point. Yeah, we didn't get through the first point in our agenda. Okay. So let's get started on our list of gods. So how is the list container constructed? That's sort of broached here, right? We've talked about the vector container. The list container has its own little bag of tricks and hazards. So lists among the most common useful data structures. Lists are among the most common. Usually a list is made out of links, where each link holds some information and pointers to other links, right? So that's this diagram here, where this is our entry point. So Norse gods is a pointer to a link. And that link doesn't point back to that, it points back to null. Right, so this is an entry into our list, but it's not the exit, right? And the entry could go to any one of these. It doesn't have to be the first one. So, well, we'll see how that all works as time goes on. So this is what's called a doubly linked list because given a link, we can find both the predecessor and the successor. A list where we can find only the successor is called a singly linked list, and we use doubly linked lists when we want to make it easy to remove an element, right? So this is not contiguous memory, right, necessarily. I mean, it could be, but why bother with a list if you have contiguous memory for that? Well, here's the answer to that question. You might want to delete something from the middle without moving everything around, right? So you can easily delete Odin here by having Freya point rather than to Odin to point to Odin's successor, and to have Odin's successor point back to Odin's predecessor. Then Odin is sort of out of the deal, right? Okay, so the structure for this is a link that contains a string, which is the name of the Norse god here in this particular implementation. And then we have a pointer. Previous is a pointer to a link, and successor is a pointer to a link. So notice that link contains member variables, which are pointers to things like it. And then the constructor says, well, I need to know what the contents of my link are, in particular what that string is. And I need to know that it, if you're constructing a link from whole cloth, which I guess that's what a constructor means, create this thing out of nothing, then you'll want it to point back to the null pointer and point forward to the null pointer, so it'll just be a single link all by itself. And then initialize these private data members. And oh yeah, these are public actually, right? Because this is a struct. They could be private. Here, depending on how you want to build this thing. But I guess what we'll do on Monday is start up right here and try to get through these exercises. But you can see this is actually a pretty long section, right? And this is where we get to this pointer. And there's more link use, and then the drill is pretty long. And yeah. I'm sorry if this is stuff you already know. You may feel like you've dealt with this. I mean, that's the hope, is that you've dealt with these kind of things, but not in this explicit detail, potentially. So let's go back. So we'll take up from there next time. So let's go back to the browser here, where I don't know why it says this. Okay, so here was our agenda, chapter 17. Well, we made some progress there. You can thank your legislature for having a half an hour less time every day, which maybe that's enough. And the n-body stuff. So think about maybe going retrograde. Legacy stuff like the pool game we were looking at last time didn't use a vector of bodies. It used a pointer to a body, right? Or a pointer to a ball. So you can maybe build your n-body problem, build a version of it that doesn't use vectors. I mean, the vector 2f, right, that we built, that didn't use the standard template library vector, right? So that's what I mean by doesn't use vectors. Don't use the standard template library vector. You can build something called vector that's your own user-defined type, or build something called body, right? And it would have, position, velocity, acceleration, mass, and radius. And it would use the new operator to allocate memory for as many bodies as you need. And that's kind of the way that pool game was built. So I'm still reading that, by the way. And yeah. Well, in any case, let me ask if there are questions before we... I guess the other thing I would point out here is that watch the announcements, because there will be new assignments as we build up towards... quiz assignments, not project. I mean, we've got this project assignment here, the n-body problem part 2, which presumably will keep you busy. Off the streets, out of the pubs, off the skate park. I think they filled up the skate park with sand. Okay, that was in LA. I don't know. That seemed like a dumb thing. Really? I mean, the idea is... the reason they had the skate park in the first place was so people wouldn't go careening off of, banisters and rooftops. So now the youth can go back to the banisters and rooftops. Joy. All right. Yeah, I don't recommend a broken bone. So yeah, you can use static cast if you get one. All right. Well, seeing no questions, I will bid you a pleasant late afternoon, evening. Yeah, you bet. And have a great weekend, too. I'm going to stop the recording. And the OBS recording.